I'm Tim Ventura from AmericanAntiGravity.com, and I'm speaking today with John Daring. John brings over 25 years of experience in applied physics and engineering to the realm of anti-gravity and new science. Well, John, can you start out by telling us a little bit about your background?
Yeah, Tim. Let's see. Consider myself to be basically an applied physicist, and I've worked for over 25 years in high-power laser and directed energy technologies, and that's included some of the standard ones like the chemical and electric discharge lasers, and I've also had an opportunity to work in some more exotic directed energy technologies, including a few that have actually been based on the idea of using part of the geophysical environment or something within the Earth's environment as part of the weapons system. I've also worked on advanced energy sources, including fuel cells and nuclear power sources, as well as, in more recent years, kinetic energy and sensor systems. Going back to the late 1970s, I started an active pursuit of what you would call anti-gravity research, and over that time I developed a very good understanding, at least in my opinion, of unified field theory and how it may apply to the problem of cracking this nut of anti-gravity. And finally, I've applied to that or extended the unified field theories to include nonlinear phenomena, which I believe are essential to understanding why so many experimenters report results that come and go, results that can't always be successfully reproduced. These nonlinear phenomena would have a threshold dependence on either power or field intensity, and unless those conditions are met identically on each experiment, this may account for why sometimes the effect is here today and gone tomorrow, so to speak. I've supervised an engineering and science team that has built 4 devices based upon different aspects of the unified field theory predictions for an anti-gravity effect, and all 4 have shown measurable force or thrust, and at least in one case we were within about 25% of the predictions of how large the force should be, which I considered to be kind of a success for the theory. At any rate, that's a little bit about what I've been doing for the last 25 years.
Oh, absolutely. Well, and that's remarkable stuff, too. Transient effects have been just a bane for this kind of research. It comes and goes, and nobody can really explain it. And so, inventors kind of come away thinking, well, what did I really see there? Well, yeah, I guess I should, move on to, some of the work that you've done. One of the constant themes in your description of anti-gravity and related effects are the description of these effects within the context of unified field theory. Can you explain what you mean by this? And
yes, you know, think about it this way. What we're trying to do, what most inventors working on anti-gravity are trying to do, is take electrical forces, which we are able to manipulate and control. After all, we have all of these electrical machines and electrical technology out there operating. The idea is to take those and apply that force, this electrical or electromagnetic force that we are able to engineer so successfully, as the lever to get a handle or to be able to do something with a gravitational interaction. Well, that's all nice, to say that, but the problem is it isn't clear, of course, how to go about doing that. Most individuals are well aware of the fact that when we turn on the lights in our house, we don't see anti-gravity effects, or when we connect the battery up to something, we don't see those effects under normal circumstances. So to really do a good engineering job and to build a system that is going to work well, we need to have some framework by which we can say, okay, we need, so to speak, this many volts or this many watts, this many amps at this frequency with this bandwidth in this type of configuration. And that is essentially asking, is there a theory or a description that allows us to make a prediction about what type of conditions would be needed in a test device in order to create measurable anti-gravity effects? The type of theory, of course, would have to be one that brings together electromagnetic forces and gravitational forces, and when you start talking about theories that combine more than one fundamental force, you're beginning to get into what are called the unified field theories, the idea that there's kind of one underlying field or force that expresses itself as the gravitational field, the electromagnetic field, and also the nuclear fields.
Absolutely. Well, you had mentioned on some occasions Einstein's unified field theory, and as I recall, you'd suggested that although it wasn't entirely complete enough for physicists to really do the work that they needed with it, it was complete enough for kind of engineering level, horseshoes and hand grenades level calculations. It,
Yeah, I think it is, Tim. And of course, even then, it requires some modification. But I'll kind of tell you what my view on that is. If you're building a radio station, you don't need to go to. And when I say build a radio station, let me explain what I mean by this example. If your job is to build the transmitter, the tower, the ground plane, all of the stuff that goes into building, let's say, an AM broadcast station, you would find that you don't need to go to the most esoteric description of the electromagnetic force. You don't need, for example, to go to quantum electrodynamics or the zero-point energy descriptions. Those certainly are valid, but it would just be a nightmare to try and work back from what is essentially a fundamental elementary particle description of electromagnetism back to something that has this engineering practicality. So what you would go for is probably Maxwell's equations, and probably Maxwell's equations in a fairly engineering-friendly form. Those would be good enough. And of course, you'd learn tricks of the trade, like how to do a good ground plane and what sort of soil conditions are most conducive to that. All of that would be folded into what I would consider kind of a practical radio engineering background. Well, similarly, let's take a look at the problem of anti-gravity. Where could we turn to get some inspiration? Not just inspiration in terms of getting a notion, but actual engineering inspiration. Well, in the late 1920s, Einstein and others worked on a class of unified field theories. These theories were later considered to be unsuccessful because they did not appear to have a simple way to bring in the nuclear interactions, that is, the strong and the weak force, and so people abandoned them. But it came as a real surprise to me about 20 years ago when, looking for some clues in anti-gravity, I began to discover that possibly those theories might be good enough, or at least extensions of them might be good enough for engineering applications related to anti-gravity. It was a rather surprising thought. I figured you might have to come up with a complete grand unified theory that described everything. Well, that's certainly a job for some of the best and the brightest theoretical physicists, but for engineering of the gravitational force, if we had a pretty good description, pretty accurate description of how to link gravity and electromagnetism, that might be good enough for anti-gravity propulsion, even though it might not be capable of describing all of the fundamental interactions that exist in the universe.
Well, John, to interject for just a second, I think what you're saying essentially is, from the inventor's perspective, from the perspective of, the guy who's out there in the field looking to modify gravity and isn't entirely sure what the relationships are, you have kind of a choice, and it might be comparable to measuring a kilometer either as meters or millimeters, and obviously the meters would be the best way to measure that, right? Is that kind of on the lines here?
Yeah, you can really, another way to look at it is this. There are interactions in nature that are very well described by certain branches of physics, which don't necessarily extend well to others. For example, Maxwell's equations are fantastically successful at describing radio wave phenomena and electromagnetism as it might apply to things like microwave systems and transmission lines. That area is well covered by Maxwell's equations. However, Maxwell's equations cannot describe the atom, because they are classical theories and the atoms are quantized, and with Maxwell's equations it predicts that the electrons spiraling around the nucleus ought to radiate all their energy away within about 10 to the minus 8 seconds and just spiral into the nucleus, and matter would simply collapse in on itself. So clearly there's a domain where Maxwell's equations are very good. In fact, they're more than good. They're great. But they're not necessarily going to describe everything that goes on. What a lot of people, I think, have erred in trying to pursue anti-gravity is they seem to think it is necessary to go and solve a grand unified theory that describes every possible force and interaction in nature. That's the job of those people working at the forefront of theoretical physics and high-energy particle physics. The job for the anti-gravity engineer and scientist is to basically find a set of governing equations that will allow them to manipulate the gravitational force, or at least what we call the gravitational force, in a way that would be suitable for propulsion purposes. One would be like doing rocket engineering, and the other is basically doing fundamental physics. They're quite different. I mean, obviously there's some crossover between those disciplines, but it is nevertheless not necessary to have a complete description of the universe in order to do this.
Absolutely. Well, you've mentioned the work of Gabriel Cron as being potentially important to anti-gravity, and this is because he derived extensions to the asymmetric unified field theory and its applications to rotating electrical machines and systems. What are some of your insights on this, and how can inventors...
Cron's work is really probably, I think, going to stand as one of the pivotal turning points. 100 years from now, I believe Cron will probably occupy a place comparable to Einstein. Now, not Einstein in terms of theoretical physics work, but at least Einstein in terms of the significance of his work to the human race. Cron was working with the problem of the effects that are seen in large synchronous motor systems in devices like power cell-sons and amplidynes. And if you're not familiar with those terms, these are basically high current rotating electrical machines that are essentially slaved to a particular synchronous signal. Effectively, these are the kind of systems that were being looked at by power engineers back in the late 1920s and 1930s for control of large, heavy machinery, but the ability to control it in a very precise way. And Cron got intrigued by the fact that many of these systems had slight defects in the way they behaved. These were effects that were known as hunting and creep, slippage, where basically there appeared to be additional interactions occurring in these motors and generators that caused them to sometimes not quite behave exactly as they had been designed. These weren't horrendous effects in most cases, but they were annoying. And so Cron thought, well, this would be a good problem for an engineer. And he was a brilliant man, so he sat down and he started applying the standard approach, which would be either Lagrangian dynamics with electromagnetism. Lagrangian dynamics, of course, is that area of classical physics that is basically the really complicated mechanical problems where you have whirling masses in different rotating frames connected to springs, those kind of problems that most graduate students have had to work through. And he also tried the Hamiltonian approach, which is used in as a similar type of approach to complex mechanics problems, with electromagnetic forces added in. And he found he couldn't get a correct description. And because those descriptions should be accurate for all physical systems, at least in the classical domain, meaning non-quantum, he thought, well, wait a second, what's going on here? These are ultimately the sort of fancy versions of Newton's laws. Well, he began to dig into it, and he found that after time he was able to develop a mathematical framework where he was able to describe these engineering anomalies such as hunting and creep. And when the smoke cleared, he found that what he had done was essentially reproduced Einstein's unified field theory. In particular, this is what's known as the asymmetric unified field theory, or sometimes these are referred to as the theories that have distant or teleparallelism, which is a condition that the geometry has. I should point out for those who are familiar with Einstein's work that this is the work that followed general relativity. This is the work where Einstein began to pull ahead of the rest of the physics community. Everyone had been with him, actually quite supportive in many ways, once general relativity was published. But from this point on, Einstein began to pull far enough ahead of the rest of the community that fewer and fewer people were taking his work seriously. And Einstein at this time actually said that these unified field theories sort of bring back something like an ether type of concept, quite different from the old idea of ether, but this appears to be actually in there, as well as the fact that these theories showed an inherent linking or coupling between electrical and gravitational forces.
Absolutely.
Cron had derived this. Cron found that these were in fact the only type of physical descriptions that could account for these effects in the motors and generators. And here's the punchline. These effects were predicted to be arising not from spurious little magnetic or electrical forces, but from the fact that that whirling machine with those huge currents flowing through it at particular frequencies and phases was in some cases inducing gravitational and torsion type fields that were producing actually additional unaccounted for forces. Now, Crone was floored by the implications of this and quickly said, well, it probably just means that the math is similar, that we're really not talking about the torsion field and the gravitational field. But it was very clear that he keeps going back in his writings and thinking, well, maybe it really does mean that. So it's remarkable that he writes a book on electrical engineering as applied to rotating systems, rotating machines, that has chapters in it on unified field theory. In fact, his unified field theory is actually more complex than that of Einstein's because it brings in spin, which is an inherent thing that is needed actually for the anti-gravity systems.
Well, in a sense, then, people could go out and pick up, hopefully they could pick up a copy of this book somewhere, but they could actually use this to engineer these systems then, right?
Well, yes, the answer to that is an absolute yes, but then here's the gotcha part. Crone's book probably is one of the most advanced books I have ever read. I've given this book to a theoretical mathematician from one of the top universities in the former Soviet Union, and he basically came back to me and he said, this guy was probably working at about the Einstein level of understanding. I mean, he wrote a book for electrical engineers, but most of the theoretical physicists that I know are unable to read that book. Oh, I mean, they can read parts of it, but the equations, it is written in a very, very complex style because, of course, these theories require a good working capability in tensors, and this is a non-Riemannian description. Remember, general relativity becomes non-Euclidean, meaning we can have the idea of curved space and time. So you hear that referred to as a Riemannian geometry. Well, this is non-Riemannian. It is a much more complex geometry. But interestingly enough, Einstein found that within that geometry, he was able to get a unification of electromagnetism and gravity, precisely what you would need if you were looking for anti-gravity forces, and Crone found that theory successfully applied to this problem of anomalous forces in large rotating electrical machines, which suggests that we are actually seeing minor gravitational effects, induced gravity effects, curvature fields, if you will, being induced in some rotating machines.
It makes perfect sense. I mean, one of the common threads has been rotating electric fields, rotating magnetic fields. And if these effects show up on a large scale in certain specialized systems, then you would also expect that from time to time you would see some of these effects, maybe not on a noticeable scale, but you would at least see them to some degree in smaller, normal systems, motors and things like that.
Yes.
Well, speaking of kind of strange occurrences, I guess, one of the things that I promised myself I would ask you about is Art's parts. And these were a bismuth magnesium microlayer alloy of sorts. Essentially just different layers of bismuth and magnesium laid over each other. They were tested by a gentleman named Travis Taylor, and he had indicated that when a high voltage hit it, it jumped off his Van de Graaff generator. Now, you'd mentioned to me that you had a little bit of knowledge that maybe the public didn't have about this, and I was wondering if you had any thoughts.
Well, I can't say a great deal about those parts, simply because I believe that there was more than one batch of parts going around. I will simply say that the one that I was able to examine was radioactive, and I have not seen that described in the descriptions that have been in various places on talk radio and whatnot. I can also tell you that the presence of those materials in there would make sense for a variety of reasons that I will comment on by simply saying that just as there are some materials that are particularly useful in electrical engineering because they have either high conductivities or high permeability or high susceptibility. I'm referring to fundamental properties of materials with respect to how they react with electric and magnetic or electromagnetic fields. There are materials that have large effects. So to kind of give an example for those that may be wondering what I mean, if you wanted to build an electromagnet, you probably wouldn't go get a chunk of balsa wood and use that as the core of the magnet. You'd probably want to go find something like soft iron or one of the ferrite materials that are very good at concentrating the magnetic field and producing a high-intensity field when you wrap a coil around it. Well, just as electrical engineers recognize that there are materials which have particularly useful properties when you want to engineer something, so there may be materials that have similar responses, high responses to what you might call the electromagnetic gravitational field. And now, these materials, of course, are probably going to display nonlinear effects, which is something we can touch on later. But the key point here is that they will act in a somewhat similar way. They may tend to intensify or in some way aid the conversion from a pure electromagnetic drive field into at least a fraction of that appearing as a gravitational field as well. So you can think of these as materials that might be useful. Possibly that's what we're seeing with ARD's parts. I'll hold off a little bit of my comments on that because I don't want to give everything away on that, but I will say those parts were very intriguing to us. I also have reason to believe that there were some that were probably, shall we say, not originals, but were reproductions of a type of part or material that might have been collected. So that would be the best way that I could describe that. That's probably really about all I can say on that.
Absolutely. Well, it makes a lot of sense. Now, that ties into kind of your idea that anti-gravity may actually be dangerous, that people experimenting with these materials and experimenting with the fields, and I believe several people have mentioned this, Hutchison among them, had mentioned that there's some really weird things happen, and these might not be the best for people in the immediate vicinity of these tests.
Well, there may be ways to partially shield some of those effects. But one of the things that I think people need to understand is we went back, a number of years ago, and we looked at a lot of these reports. There's the Hutchison effect, and of course there are a number of others which aren't actually even known to the community at large, and those are actually the most interesting ones. And what we found is that almost always people reported that there were these biological effects, and there were also oftentimes changes on the material properties of objects around that field. Now, when I first looked at that, my thought was, well, okay, that seems odd that we always kind of have these effects associated together because obviously as good anti-gravity engineers, we just want to get the force and the propulsion. Well, there's an old saying that if you pull the tail of a cat, you get the whole cat. Well, here's the problem. We're dealing at least with a part of a unified field here. We've got if you will, we're looking at the bigger picture, and we're seeing now in anti-gravity engineering that electromagnetism and gravitation are intimately one and the same. The problem is that comment I made about you pull the tail of the cat, you get the whole cat. Well, here comes the whole cat. The whole cat is you're going to get cross-coupling between all of those fields because they are, in fact, mutually inductive terms in this more complex field structure. So you don't just get a nice, pure gravitational field that's just isolated and it just produces thrust and force and everything is really nice. You're going to get an odd-looking field that is going to be time-varying. It will almost always have to be a time-varying field to really get the largest effects. You're going to see that as that field rises and falls, there will be a simultaneous increase of several different components of the gravitational field, each of which has mutual inductive relations with the magnetic and electric field terms. A lot of effects, such as penetration of things that are ordinarily shielding materials, will occur. You'll see this producing the torsion component of this links to spin, the intrinsic spin down in the nucleus of a number of materials. So you're going to see that certain materials will be affected very strongly and in an odd way. The power will be dumped in through a perturbing nuclear spin. You'll see things such as levitation effects that will appear to be maybe gravitational, but also will have an inherent electromagnetic quality to them, which might even lead some people to assume that maybe it can all be done with electromagnetism. And the truth is it can, except that you'll find that you'll probably end up invoking the gravitational terms when you try to do that. You can't entirely separate these. Now, there may be ways to produce a shielding that will damp out this, shall we say, electromagnetic gravitational field so that it doesn't produce some of the deleterious effects on people that, for example, might be riding in a vehicle using this as propulsion. But at least in the initial tests that we've seen, the ones that I've been involved in, I would say this, for a time being, is going to have to be considered as a potentially hazardous type of system to be around. I suppose maybe in 100 years, when these things are better engineered, they'll look back on this day and say, oh my gosh, can you believe they used to run those things without any shielding? They'd stand around them in the lab, just like people used to do with early nuclear reactors. Well, I suspect that there's just a lot we don't understand about the biological effects, and I suspect some of them are quite dangerous. Certainly, the effects that were reported to me on reproduction of one of the German devices were very serious. I mean, these were particularly serious on the engineer and the scientists that were engaged in that research, and I've seen some of those effects myself.
Absolutely. Well, John, this is what we like to call in the industry a cliffhanger, and we're going to conclude this portion of the interview by saying thanks for your comments on the unified field theory, Gabriel Cron's work, and I was just wondering if you have any quick comments before we close out and then later begin part 2.
Well, Tim, I just want to tell you thank you for this opportunity, and I guess what I would say at this point is that for those people out there that might have taken an interest in Cron's work, don't be discouraged. His books are quite hard to find. I don't think that's because of any conspiracy, but they've just been out of print since the 1930s and 1940s, and also they are quite esoteric. You might want to get yourself a couple of introductory books on tensor analysis and work through those, but it is possible to understand this stuff.
Well, thanks again, and we will be back in just a moment with part 2 of a conversation with John Daring.